Okay, now we're going to talk about some exponential and log applications. One of the most common applications for exponential functions is growth and decay. And so basically, if y is a quantity whose rate of change with respect to time is actually proportional to the quantity at any time t, then y can be represented in this form. Y equals y naught times e to the kt. Now, y naught would be the initial value, or the value when time is 0. The k is called the constant of proportionality, and we would have exponential growth occur if k is greater than 0, and we would have exponential decay if k is less than 0. This exponential growth formula can be written other ways. Here you could say a equals a naught e to the kt, where a naught would be the initial value. Here you could say p equals p naught e to the kt, where p naught is the initial value. Sometimes you might even see y equals c e to the kt, where c is the initial value. And this might remind you of that continuous compound interest formula in finite math, if you've taken finite math, where you have p times e to the kt. So let's look at how we might use this formula to model the population of a city. Okay, so here I'm going to go ahead and give you the model. So the population of a certain city is given by a equals 5,000 e to the 0.001 t, where a represents the population at time t and t represents the time in years. Okay, the first question is pretty simple. Just find the population at the end of 5 years. So we just need to know the population when t is 5. So we take this function, and for t we just plug in 5. And then so we have e to the 0.0015 times 5, which is just 0.005. And then we just calculate this 5,000 times e to the 0.005. And that's just 5,025. So it's growing rather slowly here. Now, the initial population, if you want to know here, remember the initial population was this constant here, 5,000. So basically it grew from 5,000 to 5,025 over 5 years. The next question says, how many years until the population doubles? Well, since we know the initial population was 5,000, for the population to double, we would need the new population to be 10,000. And we want to solve for the variable t for that. So what I'm going to do is I'm going to just plug 10,000 in for the amount and then solve for t. So if I divide both sides by 5,000 here, so because what I want to do is I want to isolate the exponential expression first. So divide both sides by 5,000. Well, 10,000 divided by 5,000 is 2. And the right-hand side divided by 5,000 just eliminates the 5,000. Well, now I can take the natural log of both sides, and I know the natural log of 2 is just natural log of 2. But what's interesting is since this is base e, the natural log of e to a power is just the power. So the natural log of e to the 0.001t is just 0.001t. So now to solve for t, I just take the natural log of 2 and divide it by 0.001 to get t. And when I plug that in my calculator, I got over 693 years. So it's going to take quite a bit of time. Now, the guidelines for solving exponential growth and decay are basically you're going to use the given information to write two sets of conditions. This usually indicates the initial condition or the condition for when t equals 0 and a later condition. Then we'll use the initial condition to solve for the constant. The value when t equals 0 is the constant. Then we'll use the additional information to solve for the constant, and then once we have the constant, we can use the model to answer further questions. Now, something you might find interesting, if you do a search online for population clock, you'll find sites that actually use this type of model to approximate growth or decay of a lot of different variables. So you can just take a look if you want to and see what you can come up with. All right, now let's take a look at this example. In the year 1900, the population of a city was 12,500, and then 20 years later the population was found to be 16,000. Well, the two conditions that I'm given is basically that when time equals 0, which is the year 1900, I get 12,500, and then when time is 20, I get a population of 16,000. Well, to create the model for this, I'm going to need, first of all, the initial population is 12,500. So I'm going to use this P equals P naught e to the KT. That's what I'm going to use. Now I know that P naught, the initial population, is 12,500, so that would go there. And now I need to find the K. Well, that's where this other information comes in. I know that P must be 16,000 when T is 20 years. So I can plug in 16,000 for P into this model and then plug in 20 for T, and so I'll get 20K. I prefer to write it as 20K instead of K20. So now if you divide both sides by 12,500, 16,000 divided by 12,500 is 1.28. And then on the right I just have e to the 20K. Well, then I can take the natural log of both sides, and I know the natural log of 1.8 would equal the natural log of e to the 20K. But I know the natural log of e to the 20K is just 20K, so I have the natural log of 1.28 equals 20K. So K would equal the natural log of 1.28 over 20. And in the calculator, I took this out to 4 decimal places, and I got 0.1234. So now the completed model is P equals 12,500 e to the 0.01234 T. I think up here it's supposed to be 0.01234. So it's 0.01234 T. Now, if I plug this information in, if I use this function, now I can find the population at the year, estimated population at the year 1950. So the 1950 would correspond to T equal 50. So I would plug 50 into the function and then just solve this function when T is 50. So I get 12,500 equals e to the 0.01234 times 50, and I get 23,167 is the population. So now the third question says estimate to the nearest year when the population will reach 37,500. So I'm going to take this model and I'm going to replace P with 37,500, and I'm going to solve it for T because I want to solve for T now. So 37,500 would equal 12,500 e to the 0.01234 T. And then if I divide both sides by 12,500, I get 3 equals e to the 0.01234 T. Well, now I can take the natural log of both sides. So I get natural log of 3 equals natural log of e to this power. And the natural log of e to that power is just that power, p of 0.01234 T. And then to solve for T, just divide natural log of 3 by 0.01234. And I get 89.02 years. And so near the year 1989 is when I would expect the population to grow to 37,500. Another example of exponential growth and decay is finding the half-life is half-life problem. The half-life of a material is the amount of time it takes for half of the material to decompose. For example, if the half-life is 10 years, after 10 years half will remain. After 20 years, half of half, or 1/4, remain, and so forth. So here I'm given that the half-life of radioactive material is given to be 20 years, and then an initial amount of 80 kilograms of material is to be disposed. And so I want to construct an exponential model that gives the amount of material remaining after T years. So I'm going to use this formula, A equals A naught e to the KT, where A naught is the initial amount. So since the initial amount is 80, I know A equals 80 e to the KT. Well, I know that since the half-life is 20, then when t is 20, only half of that initial amount will remain. So A will be 40. So I can plug in A equals 40 and then plug in 20 for t, and I get 40 equals 80 e to the 20k. Well, then divide both sides by 80. 40 divided by 80 is 0.5. So I get 0.5 equals e to the 20k. Then I can take the natural log of both sides. Natural log of 0.5 is equal to natural log of e to the 20k. And since the natural log of e to the 20k is just 20k, I get natural log of 0.5 equals 20k, and then divide by 20 to get natural log of 0.5 over 20. And so now I have the k value, negative 0.03466, and that gives me my completed model. Now from that completed model, I can answer the next question, which says how much of the material will remain after 200 years. So all I have to do is plug 200 years in here for t. There's a t right there. In here for t, and then I'll get 80 times e to the negative 0.03466 times 200, and I get that only 0.078 kilograms will remain, is expected to remain. So theoretically, it never all decays. Let me show you some interest formulas here, and then I'll in the next video I'll show you some more of the outlier type formulas you might run into. So here we have $22,000 is deposited into an account paying 7.5% compounded quarterly. How much money will be in the account after 12 years? So basically what you want to do is plug in the information into this formula up here. We know the principal's 2,000, the annual rate is 0.075 in decimal. We're compounding quarterly, so n would be 4, and since t is 12 years, we'd have 4 times 12 for the exponent. And you just plug that in your calculator and you get 487832. Well, the next question says, how long will it take that to grow to 10,000? So what I'm going to do there is I'm going to replace A with 10,000 and solve for t. So I have 10,000 equals 2,000 times 1 plus 0.075 over 4 to the 4t. Now, if you add all this together inside this parentheses, you'll find that it's really just 1.01875. So that's where I got the 0.01875. I just figured out what this was, and then I added it to 1, and I got 1.01875. And also, I divided 2,000 into 10,000 to get the 5. So I have 5 equals 1.01875 to the 4t. Now I can take the natural log of both sides, so I have the natural log of 5 is equal to the natural log of this. Now this isn't a base e this time, so I can't just simply eliminate the base. I have to say, well, this is equal to, I can bring this down and say this is 4t times the natural log of 1.01875. And then to solve for t, I have to divide the natural log of 5 by 4 times the natural log of 1.01875. And make sure you put the bottom in parentheses. And I got the answer was 21.66 years. And then on continuous compounding, if I do the same thing for continuous compounding, then you would actually use this formula. And I'll let you answer the first question. It's pretty simple. The principal is $1,000 and t is 20 years, so you just plug that into the formula. And then it says, how long will it take it to double the initial investment? Well, the initial investment was 1,000, and you want it to double, so you put 2,000 for the amount. Then you just solve this, divide by 1,000, you get 2 equals e to the 0.06t. Then take the natural log of both sides, and then you're going to get natural log of 2 equals 0.06t, and then divide by 0.06 to get t. So it takes about 11.6 years for it to double. So on the next video, I'll do some examples that are kind of off the beaten path that have to do with log and exponential equations.